trending stuff in the VLSI. It is design verification. I am G. Akshay Kumar and working as a front-end design front verification engineer. So in this session, we will discuss about what is a design verification, what is design, how the evolution of Verilog, SystemVerilog, and UVM comes into picture, how Verilog will be useful, and we'll see one by one. So this is how a ASIC flow, like how a chip can be come to market. What are the steps a chip going through this ASIC design flow? So these are like software. We have front end as well as back end also. This design verification comes under front end design. Okay. So this green part will be the front end, and next is orange part will be the back end part. Back end mainly involvement of physical design stuff. So let's discuss like what are the each and every steps and what is the role of each and every steps. So first is design specification. So first one is design specification. Like what is the meaning of design specification, why it is used? So before going to implement any design, there is a set of rules. Okay, so if you take any protocol or like APB, AXI, or anything, before going to implement in your code, you need to go through some set of rules and set of features as a part of RTL design engineer, as well as a verification engineer. If you are verification engineer, you need to point out some test cases, like, yes, what are the things I need to test, which features I need to test. For each and every feature you have a specific test cases. These can be decided through design specification. This is nothing but a set of rules. Okay, now it comes RTL description or HTL. So now the role of RTL design engineer will be like, what are the uh, content, what are the features are extracted by the design specification that will be implemented in the Verilog by RTL design engineers. Okay, so if once RTL is ready, RTL means your design is ready, you will forward it to verification engineer. Okay, this is a functional verification. Verification engineer will first go through the set of technical documentation of the RTL design engineer, and he will point out each and every features. What are the features I need to verify? Okay, so based on that features, the verification engineer will first do the test plan. Okay, once a test plan is done, based on the priority, it will execute one by one. If for example at particular any test case, your expected result is not matching with the RTL, so it will file a bug to the design engineer, like in a particular scenario, in the particular case, the output is not expecting, the expectation output is not matching based on my test case. Okay, that's why if no, then it will go to RTL description. If it is yes, once verification engineer done all the test cases, all the test cases are passed with the expected result, then it will go to the backend part. So these are the backend scenarios, like mainly physical design. This is logic synthesis. So it will check like whether the synthesizable code in the design or not. Then it will go to gate level netlist. Gate level netlist means whenever you are written a code in the Verilog, right? These are the simple English code that will be converted in terms of gates, muxes. That is called gate level netlist. This one. Once it is done, then this logic design will done. Then you go to the logic equivalent check, and then place and route. So this is the proper physical design, placing and routing. So I have no much idea in the physical design. So I have working on this front end part. So basic I can share with you people. Like place and route means we have some core dia area is there. You need to place the transistors and you need to do the routing. Okay, After that, then it comes the physical layout. Then it comes to, again, this is physical verification. That is, functional verification means your front end verification. This is a physical verification. If any bugs during placing and routing, then it will place a raise a bug to the physical design team during placing and routing. Once the physical verification is done, this is the final process. Once physical verification is done, then it will jump to GDSI. Then the chip will go for manufacturing. Then after fabrication, your chip will come out from the lab. So how this is the flow, like how a chip can be come into the market, like both front end as well as a back end design. Okay, we will move forward. Like, yes. So introduction to Verilog. So prior to that, anyone having any idea on Verilog? Verilog is used for design verification purpose. Okay, so mainly we cannot prefer Verilog for verification. So nowadays, are very uh, useful in the market is UVM for verification. Okay, you can verify basic simple circuits in the Verilogs. Okay, so when it comes to Verilog, there are three modeling techniques. That is gate level modeling, structural level modeling, and behavioral level modeling. So we will see the code description one by one. See, like what is design and test bench in the Verilog? Normally in the C language, hope you can able to see this test bench and design part. So for example, this design is a simple C language code. So hope you can able to uh, understood this basic logic, whatever placed in the design box. So let's assume this is a C code. Okay, and the inputs are driven by user in the C, like scanf and all. But here your user will be the test bench. Through test bench, you will drive the inputs to the design, and through design you will give the output to the test bench. So let's see, this is the very simple logic I have written in the design part. So just consider, just remember, just forget about this always. Okay, these are the inputs a, b, and select line. This is the output out variable. If select is 1, addition. If select is 2, subtraction. If select is 3, multiplication. Else don't care. Okay, so design needs three inputs. The three inputs are yellow lined. Okay, this is from test bench to design: a value, b value, and select value. Based on these three stimulus, design will perform the action and it will throw a output. So what is the output? 5 plus 3, 8. This is the green line. It will show the output from design to test bench. So once we have received the actual output in the test bench, we can verify like whether I have received the correct result or not by writing our own logics. Okay, so that's called a self-checking test bench. So whatever logic you have written in the design side, a basic logic will be written in the test bench side. Okay, if select is 1, then expected value will be addition. So instead of 8, if you receive 6, then your design having some errors. Okay, so how the design and test bench will be differentiate to each other, and how it is different from your software language, C language. Okay, so hope you are understood this design and test bench concept. We'll move forward. Okay, so what is the program structure in the Verilog? So normally when it comes to C language, you are like you are writing int main, open braces, curly braces. Inside that you are writing your own code and logic, right? So here you're writing module. Module is the keyword. This is constant. This is the module name. You can write anything, module name. This is a port list. We have previously shown this design, this module having port list. What are the ports? Input are A, B, select line. Output is out variable. Okay. So these are the port description you need to mention in the bracket. Which variable are the input to the design, which are output from the design. Okay. So once you have written in the post port list, then you can write, you can declare like which port is input and which port is output. Okay. Then it comes to module item. Module item is based on your logic. What logic you want to write, and end module. These things are constant. Okay. And in the C language, we are writing open braces, curly braces. Okay. These things will be replaced with begin and end in the Verilog. We can write begin and end is the open braces and curly braces in the Verilog. So module name is, it is an identifier that uniquely name the module. Like you are writing two modules, but your module name should be different. Okay. So your module name should be unique to each other. Then it comes port declaration. Okay. What are the inputs and outputs? What I have written in this slide like this. Okay. So let's see what are the styles of modeling in your Verilog. We have structural modeling style. These are the various coding style in the Verilog. Data flow modeling style, behavioral modeling style. So we will see briefly what are the three things and how they are different from each other through code. So hope you people are aware of half header, right? So it will be easy if you take example with half header. So when it comes to structural modeling now, you need to represent this XOR. These are the keywords used. Okay. Like in C, break and continue are the simple keywords. Here, XOR, this will be act as XOR gate. A and D, and will act as AND gate. Okay. So this is in structural model. We will write like this. See, this is the module is simple. This is constant. Half header structural is the module name. Okay. These are the inputs. What are the inputs we have? A, B, and sum and carry, S and carry. XOR the XOR gate. This is the gate one is the name only. So for this gate, I'm mentioning gate one. For this gate, I'm mentioning gate two. Instead of gate one, you can write G1, G2, X1, anything. This is the user defined. Okay. So your syntax will be output, input, input. For XOR gate, you have sum is the output, A, B are the input. Okay, exactly for AND gate, C is the carry. Okay, carry is the output, A and B are the input. This is the one of the coding style in the Verilog, that is structural modeling. Okay, your structural modeling is done. Then we'll move forward to data flow modeling. So just remember, in the structural modeling, we are writing these keywords. Okay. When it comes data flow modeling, everything is same. You are dealing with your symbols. Okay, XOR, and in the data flow, you will deal with symbols. Assign S equals to A XOR B. Okay, whatever this A value, B value, who will provide the value of A and B? Through test bench. Through test bench, you will give the input or stimulus to the design. What is the value of A? What is the value of B? And output will throw the value of S and value of C. Okay, sum and carry. So hope you differentiated between structural modeling and data flow modeling. Now we will see the behavioral modeling. So behavioral modeling is involvement of a truth table logic. So based on truth table behavior, you need to mention the code. You need to write your own logic. Okay. So up to this one is same. Module half header behavioral is the module name. What are the inputs and what are the outputs? Okay. So this one is always at the rate star begin means whenever change in the any input, we can say this is a loop. Okay. We can say this is a loop. Star means whenever any change in the input. For example, at initial at 0 nanosecond, A is 10, A is 1, B is 0. Okay, after 10 nanosecond, I'm giving A is 0, B is 1. You can see, right? Your A value and B value is changed. A value, B value is changed means your always block is triggered and it will go inside the always block. Okay. And rest logic is same I have copied from truth table. If A is 0, B is 0, sum is 0, carry is 0, exactly for all 0 1 1 0, and last one is else, only one possibility, that will be A equals to 1, B equals to 1, then your carry will be 1, sum is 0. So hope you understood. This is these three things are from design side. Okay, these are the three various modeling techniques in the Verilog. So up to this, we have covered basic introduction of Verilog and basic modeling style in the Verilog, and hope you people have understood like why the Verilog is comes into picture. Now we will move forward to the system Verilog. Like what is system Verilog, how it is different from the Verilog and all. Okay. So this picture is very much clear. Like in system Verilog, these are the extra things are added. Okay. So when it comes to Verilog test bench, the very less features have in the Verilog, and it's very difficult to verify very complex circuits. Okay. So in system Verilog, we have various different techniques. Like you can able to see, we have oops, constraint randomization, functional coverage, these things. Okay, let me discuss very briefly each and every one. One is oops. Like hope you are aware of oops, object-oriented programming language, same as Java, C++, and Python. Exactly. So this oops is introduced in the system Verilog. Through oops, your code reusability is very higher with the help of inheritance. Okay. So if you are aware of inheritance, it will be good. So in when it comes to Verilog, we don't have any scope of oops. Okay. So when it comes to very complex design, it's very difficult to verify. Then it comes to your constant. Then it comes your constraint randomization. So just remember, for example, I want to uh, generate a random value between 10 to 100, and I want to assign to a variable a. Okay, I want to generate a random number from between 0 to 10, and I want to assign to a variable called a. So these things will be not happened in the very long. There is no support of this, but through this constant randomization you can do. So this is a very good feature added in the system Verilog, that is oops. So we have various things like inheritance, abstraction, like Java only. So these things are comes into picture. So oops and all. So through this you can give reusability. The code, your code will be protected. Okay. Okay. Now we will see the entire discussion is going on design verification, design verification. So what is the actual meaning of verification? So if I say in the layman point of view, you need to verify each and every features of the design with various possible scenarios. Okay, so this is a very basic and simple example. So you can see one error is there, like one um, error is there in this code. Can you find out like what is the error in this code? So you can see the sum expression for the half header will be A XOR B, right? But due to some reason, by mistakenly, the RTL designer is placed OR instead of XOR. Okay, and your module is ready, your design is ready. Now it came to verification engineer, and verification engineer need to test whether the half header module is behaving correctly or not. Okay, so our definition says, the verification definition is, you need to verify each and every uh, uh, scenarios with different test, each and every features with different test cases. Okay, see, so this is the truth table for half header, right? So as a verification engineer, I'm verifying through these two stimulus only. Okay, so just consider two sum. I'm giving through test bench, I'm giving A equals to 0, B equals to 1. There is no issue, sum will give 1 based on truth table. It's correct. Okay. And now I will drive another pair. A is 1, B is 0. Still, sum will give 1. So there is no issue. It is matching. Okay. Now I will conclude that design is working properly. If I forward it to design team, your design is working properly. It's wrong. You need to verify each and every corner scenarios. Okay, instead of two pairs, if I give all four pairs, okay, these two pairs are verified. It's output is as expected one, it is coming. When it comes to 0 0, if I give A equals to 0, B equals to 0, what will be the sum expression? A or 0, or of 0 0 is 0 only. Yes, your sum is correct. But if I give fourth pair, A equals to 1, B equals to 1 to the sum, what is the OR of 1 and 1? That will be 1. But your design will throw 1 and 1, your that will be 1. Your instead of sum 0, the design will throw sum as 1. Okay. Now you have found out a bug in the design. So when it comes to fourth pair, A equals to 1, B equals to 1, your design is giving wrong output. Okay, you can file a, error or a bug against this half adder module. Like when I'm applying 1 1 test case, I'm getting 1 instead of 0. Okay, this is a very simple uh, verification I'm telling. So when it comes to very big verification, and then you need to think in different way. Okay, so you need to verify each and everything through test cases. So we just assume these are the four test cases, and design is failing at fourth test case. Okay, then design engineer will see what is the problem with sum, then they will modify. Instead of or, they will put XOR. Then again the verification happens with four test cases: this pair, this pair, this pair, and this pair. When it changes to XOR, your verification is completed, your design module is completely working. This is a very simple example for verification. Like what is verification, like how a verification happens with various scenarios. Okay, verification is a process to make sure that design is working as expected or not by applying various scenarios. These are the four scenarios in this case. Hope you understood like what is verification and all. So we will move forward. See, when it comes to Verilog, we don't have any particular architecture. In the Verilog test bench, it's very simple. If you have inputs, just assign A equals to 10, B equals to 20, and expect the output. That's the very simple. If you have a simple design, then it's fine. Verilog can help, but when it comes to a complex designs, this system Verilog test bench will be helps a lot. So through this system Verilog test bench, you will verify. So see what are the present right side of this interface. Right side of the interface is DUT. DUT means your simple design code. Let's assume simple half header design code. Okay, and whatever present left hand side of the interface, that is your test bench. Test bench architecture in system Verilog. So these are the layer test bench you can see. So when we start coding, then you can able to get a clear picture. But as of now, just remember how the SV test bench look like and what are the components are involved and what are the connection. That we have test, env means environment, we have agent. Inside the agent, we have a generator, driver, monitor, and inside the environment, we have a scoreboard. So just we will discuss a brief about each and every components. Okay. So just assume we have half header is connected with this test bench. This DUT is replaced with half header. Okay. This generator means it will generate the various stimulus. Various stimulus means this one. What are the value of A? What are the value of B? What are the value of A, B? Okay. These things will be generated by generator. Okay. Then whatever things are generated, that will be processed to driver through a mailbox. So when it comes to system Verilog, you can know. So just as of now, just remember mailbox is a process to transfer the data from generator to driver. Okay. Once you have data with driver, the data will be transferred to interface, and interface will drive the data to your half header code. Okay. So interface is nothing but connection between your test bench and design. Okay. Your driving is done. So for example, generator is generated, A value is 1, B value is 1. That will be transferred to driver, and that AB value is transferred to design. Design will process. If A is 1, B is 1, sum is 0, carry is 1. That will be driven by design to test bench. Okay. Through this, it will go to monitor. Monitor in the sense, just it will monitor whatever, just it will monitor the things, whatever the things are coming from design to your test bench. Okay. Once the sum and carry value is received, that will be transferred to scoreboard. Scoreboard is nothing but a comparison. So whether is correct output is coming from DUT or not. These things and these logics will be there in the scoreboard side. Okay. So this is the how a entire test bench is built in the system Verilog to verify a design. Okay. So half header, full header are the simple. We can verify through Verilog. But when it comes to very big designs, then your system Verilog will help a lot. The system Verilog architecture. So we can see in system Verilog, we have various data types. Okay. So when it comes to Verilog, it's very less data types. We have reg, wire, integer, real, dollar time. That much. Very limited data types. When it comes to system Verilog, we have various data types having 2 states and 4 states. So the meaning of two states is the output can be 0 or 1. Four state means it can be 0 or 1 or x or z. X is don't care, z is high impedance. Okay, so this is the size bit. Okay, bit is the only, it will, if you write bit x, then x will x having one bit size only. And bit x down to 0 means uh, I want to assign 8 to a variable a. So the a should capable of 4 bits, right? So to represent 8 we need 4 bits minimum. So in that scenario we will write bit 3 down to 0 a. That will be helpful. That what the meaning? Bit 3 down to 0 a means a can capable of 4 bit data. 4 bit data means from 8, from 0 to 50. Then a byte is itself 8 bit. Okay, if I write byte a, then I can assign 8 bit value. Then sort int is the 16 bit, int is the 32 bit. And this int is not supported in the Verilog, right? Only integer integer is the supported in Verilog. This is the long int 64 bit logic rich integer this integer is supported in the Verilog. And this is the time and real. Okay, so these are the various data types are supported in the Verilog. When you see in arrays in software also, we have only single dimensional array and multi-dimensional array, but when it comes to Verilog, we have various arrays: packed array, unpacked array, fixed array, dynamic array, queue array. Okay, so I can tell like fixed array means once you declared ARR 5 means your array will be capable of 5 data only, 5 number of data only. But when it comes to dynamic, we can say it is dynamic in nature, fixed array, static in nature. Okay, so the difference is the fixed array will get memory during the runtime, sorry, in the compile time. Dynamic array will be in the runtime. And queue array, so you don't have any size for queue array. So if I push 8 values, then queue array size will be 8. If I push another 8 value, the queue array size will increase to 8 to 16. Okay. And associative arrays, like uh, we can we can store any value in any location. Okay. So these are the various arrays we have in the system Verilog. If you compare with Verilog, in Verilog we have only single dimensional array and multi-dimensional array. Okay, so we have various features, various data types, various uh, Verilog arrays. Okay, so up to this is the discussion of system Verilog. So we have just go through on what is system Verilog, what is verification, how verification happens in the system Verilog data types, and system Verilog arrays. Now it comes universal verification methodology, that is UVM. So you can't say UVM is a new language. It's same. You can say it is a system Verilog, but some modification. So to be in same page, the people are decided to make a common verification language that will be helpful. That's why it is named as universal verification method. So we can say 3 boxes. Okay, this is the combination of a system Verilog and system Verilog concepts and own UVM methodology. UVM added some extra features to the test bench. Okay, test bench architecture is same like this, same as this, but some slight changes is there in the UVM. Yes. So whatever syntaxes are there in the system Verilog, same it will follow. UVM also same. So that syntax, oops, interface classes, same as system Verilog only. And when it comes to verification concepts, I have discussed this constant random, right? Constant random. These are same. And UVM methodology added some extra features, like we can say phases. Phases is there, one concept in the UVM. So it will be help a lot during the compilation and during writing any test bench. Okay. So universal verification methodology, the combination of system Verilog language, system Verilog concepts, and its own some new concepts. See, so hope you can able to remember, compare with SV verification test bench and UVM verification test bench, exactly same, but instead of generator now it is sequencer, and sequence also there, it is not mentioned. Okay, rest remaining the same. Interface used to connect test bench and DUT. Okay, same scoreboard, the role of scoreboard is to verify. Okay, so it will be like better, like if you see some basic code, it's basic addition code in Verilog. Okay, design and test bench. So see, yes. So hope you can see this is a very simple code of half adder in the structural modeling. See, this is the I have discussed already. Input A, input B, output is some carry, and XOR is a keyword. It will act as XOR gate and act as AND gate. These are the gate names only. Sum is output, A and B is the input. Carry is the output, A and B is the input. So how the test bench will look like? See, what this is a module TB. Whatever uh, values, whatever input have in the design, that will be act as reg. Okay, in the test bench side, and whatever output will be there in the design side, that will be act as wire. Reg wire are the two data types in the variable. We can discuss like why this is reg only, why it will be wire only. Okay. So this line number 7 will be the instantiation. Instantiation means like how this test bench and design can connect. Okay. So half header. Why it is half header? This is because of this module name is a half header. That's why I have written half header. Okay. This DUT is the simple name only. Okay. You can write XXX, BBB, CCC, anything. Just I have written DUT. And these are the port connection. Okay. So here A will connect with A. Your port connection must follow the same rule. Input, input, output, output. Here also input, input, output, output. Okay. Once it is done, the connection is done. Then we will see, just remember this line 10 and 11. At line number 14, you are driving the stimulus, various stimulus, A equals to 0, B equals to 0, A equals to 1, A equals to 0, B equals to 1. After some nanosecond delay. Okay, like this. And we need to print the input as well as output. That's why I have used this monitor. Okay. So this same syntax like C language only. Percentage B represent binary. Okay. So these are the A, B, some carry will be printed. If you run this one, so hope you can see this one. If you want to see the timing also, just you need to put See at 0 nanosecond. See at 0 nanosecond, A equals to 0, B equals to 0. We will see whether at 0. See at line number 14, at 0 nanosecond, A equals to 0, B equals to 0. The expected result will be sum is 0, carry is 0. See, your sum is 0 and carry will be 0. At 10 nanosecond, at line number 15 and 16, A equals to 0, B equals to 1 are driven from test bench to design. Okay. A equals to 0, B equals to 1, and sum each one, carry each 0. Correct? Exactly for 20 nanosecond, A equals to 1, B equals to 0, your sum is 1, carry is 0. Exactly for 30 nanosecond. Same. Okay. So this is how a basic simple half adder code in structural model. So we can see in the data flow or behavioral modeling style, etc. Okay. So yes, this is from my side. So the basic discussion of Verilog, SystemVerilog, and UVM, how they are used and all. So is there any questions?
Sir, in industry, which tool you are using for verification specifically?
Okay, which tool you are saying about?
Yes.
Yes, normally we can use for verification also. We can use this EDA playground only. Okay, through EDA playground we can use up to UVM also.
Uh, no, for when hardware is very complex,
Yes.
circuit is very complex, na? You won't be using open source. I'm just curious.
Okay. So if uh, circuit is complex, then we can move to system level verification. So everything is supported in the EDA playground tool only. So apart from EDA playground, we have QuestaSim also. Through QuestaSim, we can do the verification, and that will be easy to see the waveforms clearly. When design will complex, your verification methodology will be different. It can be a system verilog or it can be a UVM.
Okay, yes, sir.